Thank you, Chairman. Good morning, everyone. My title is a study on the concept of utilizing lift and escalators in the evacuation route using fragility assessment. In this time, I'd like to talk about the damage analysis and the pedestrian simulation. Currently in Japan, the lift and escalators cannot use for the evacuation route. This is a just simulation for the examine the evacuation time by using the escalator and the lift for the evacuation route. And also this research result is conducted by the master course student in my laboratory, Mr. Nakajima. But unfortunately, he could not attend the symposium. So I will explain instead of Mr. Nakajima. Okay. So Japan has a lot of huge earthquakes in recent years. During strong earthquakes, the walls, ceiling, pipings, electrical cables, and various equipment in the building are damaged and drop out in the floor. Such damage is seismic damage to equipment and the other facilities in the buildings had a significant impact on the evacuation route. Example, if the strong earthquakes occurred in this room, the ceiling and the electric equipment may fall down on the floor. But in Japan, the people need to be attention for such seismic damage in our daily life. So before I explained earlier, the lift and escalators cannot be used as evacuation routes. However, the strength and the capacity of the lifts, escalators, equipment, and especially a joint part, that means the connecting part to the architectural structures, it can be understood with a very high degree of accuracy based on the latest advances of expert knowledge in structural analysis techniques and accumulation through the shaking table test using full-scale test specimen. So that means that we can estimate in a high level accuracy of the fragility of the equipment for the evacuation route. The few studies have considered the building and the facilities as a single system and examined the maintenance of a system function during severe earthquakes. So this is examining the concept of the appropriate evacuation route based on the pedestrian simulations, considering damage events to mechanical structures related to the selection of an evacuation route. We can consider such contents in this presentation. And pedestrian simulation in 40-story high-rise buildings are conducted to quantitatively evaluate the time required to complete evacuation and to analyze the effectiveness of using lift and escalators for rapid evacuation. First, I'd like to show you the fragility assessment. The fragility assessment is one of important and convenient method to evaluate the seismic damage of the equipment quantitatively. And fragility curves, it means the seismic damage of the equipment obtained from the probability density function of a response and also the capacity. The seismic damage means an event that occurs when the value of a realistic response exceeds the value of a realistic capacity of equipment. In this figure, the red area means the seismic damage probabilities. And also, in this time, we consider the conditional probability for specific damage status as shown in this table. The mode 1 means the no damage, and mode 4 the serious damage. In each table, we can obtain the fragility curves and the probability distribution in each damage mode. So next, I'd like to show you the example of fragility curves of the equipment. As shown in these pictures, the suspended settings have a large installation area like here, and so damage such as falling off may cause serious damage. And the clips, this here, the weakest component of the suspended setting are the focus on the analysis as an example. The damage conditions summarized in the table and the analytical model is shown in these figures. In this time, the mass part of a suspended setting is modeled as a 1 degree of freedom system, and the capacity of the clips is investigated from the response analysis using 1 degree of freedom systems. And as a result, setting damage probability of a clip summarized as shown in the table. In this case, the seismic wave is the El Centro NS and the JMA Kobe NS. It's a very famous input wave for the seismic design. And fragility curves are obtained its figures in each damage mode. This picture shows another example of the suspended equipment. This equipment is also sometimes drop off in the severe earthquakes. The causes are low cycle fatigue of still hanging materials due to equipment shaking and disconnection of joint parts. In this time, the damage condition are summarized in this table, and analytical model is shown in these figures. So the suspension length of 800 millimeter and 4 bolts, and the equipment weight of 20 kilograms. As a result, as the same before, the setting damage probability of hanging equipment are summarized as shown the table and the figures. Next, I'd like to show you the influence coefficient from pedestrian simulations. The generalizing pedestrian evacuation route against obstacles and understanding the trend of routes according to the size of the obstacle and the degree of path dominance will contribute to the improvement of the evacuation safety from the stage of designing equipment layout in the buildings. So the pedestrian simulations were used to consider the possible bypass route for obstacles, and the impact of obstacles on evacuation route was calculated as the influence coefficient. There we can see these figures. The blue line shows the detour, and the black line square is the obstacles. In the simulation, we used an evacuation route considering a passing gate 2.5 meter wide and 10 meter long, divided into 15 and 60 cells. And the influence coefficient are determined from the ratio of the simulation result to the straight through time in the absence of obstruct. The evacuation route for each damage mode, assuming a setting fall, the setting panel was assumed at 1.8 by 0.9 meter. Several patterns of evacuation route are derived from the simulation. From the simulation results, the bypass patterns for each damage mode are shown in these figures. The mode 2 and mode 3 and mode 4, there are several patterns of the same damage, seismic damage. And we can see the evacuation route pattern. This figure differs the starting point of the evacuation point. In this case, the damage 2 and damage mode 3 and the damage mode 4. As a result, the influence coefficient summarized in the table. And the influence coefficient, the 0 means the passable without obstacles, any obstacles, and 1.0 means totally impassable conditions. Another example, the hanging equipment, mode 3, mode 4, and also the float glasses in the window in the mode 3 and mode 4. We consider such seismic damage of equipment for the pedestrian simulations. The explanation so far is for the two-dimensional evacuation route. That means the floor level. But the next slide shows the three-dimensional evacuation route. In high-rise buildings, the seismic response differs between the low, middle, and high-rise floors, which may result in various types of damage to the installed equipment. The evacuation simulation is simulated by the pedestrian simulation on each floor, and the target building is 160 meter and 4 meter story height, and the dimension of each floor are set to 40 by 40 meters. And the floor map for each floor, each floor, or 10 floors, the layout diagram for each of the 10 floors showed. Each floor has two staircases here, and 2 escalators here, and 2 lifts here. The total of 100 evacuees are assumed for each floor, and the total of 4,000 evacuees are considered in the building for the pedestrian simulations. The cells in each cell divided into a floor map grid are numbered, and the simulation is performed by moving to a cell with a smaller number than the current cell. The walking speed of evacuee is 1.00 meter per second. This is an estimated value, and the staircase movements are considered in detail, and time required for the evacuation is calculated. The delay time due to stagnation propagation is assigned as a variation of the evacuation time using a model for the occurrence of stagnation phenomena caused by the human congestion at staircases entrances and in staircase rooms. Based on the setting of the various parameters, the occurrence time and the transition of the number of the people in the 3 states of stagnation, start of stair descent, and end of stair descent are calculated. It can be seen that the time required to complete the evacuation increases as the input wave becomes stronger. The horizontal axis means the input wave level of the seismic input, and the vertical axis is the evacuation time. So the delays occur after reaching the stair at more than 25 minutes pass before everyone evacuate. And next slide shows the simulation of evacuation by using the escalator. In the fragility analysis for the escalator was already reported in a previous symposium, this symposium. So please refer the fragility analysis for the escalator in the report. In this time, the escalator travel during evacuation is assumed to be accompanied by walking. In this case, the speed of the escalator is 0.5 meter per second, and the speed walking on the stairs is 0.6 meter per second. By combining these two speeds, the speed of movement using escalator is assumed as 1.1 meter per second. The length of the escalator is assumed to be 8 meters. And next slide shows the simulation of evacuation by using a lift. This is not a fragility analysis. In this study, the lift are assumed to move in such a way that they stop every 10 floors and the door is open and closed. The lift assumed as a 22 passenger lift, and transfer time is assumed to be a door open, close time, plus transfer time from another stop floor, plus door open and close time. The specification is summarized as a table. And as a result, the blue line shows the use of stairs only, and the gray line means the use stairs and the lift, the combination. And the orange line shows the use stairs and escalators combination. And also the yellow line shows the use stairs, escalator, and the lift, all of combination. It can be confirmed that the use of multiple means of evacuation allows for faster and safer evacuation, and the time saved by using only the staircases and using all the evacuation route is about 300 seconds. And finally, I'd like to show you the conclusion. As a result, it was confirmed that using both escalators and lift for evacuation routes can reduce evacuation time by approximately 70 seconds for every 10 floors in the analytical specifications. That's all. Thank you very much.
That was fascinating, and later on I think I've got lots of questions about the simulation and the assumptions that went into that and how you modelled it and the evacuation lifts and what have you, but we'll do that later. I think we've got time for just one question if anyone's got one. No, I can't see any hand. Oh, right. Where's fire away, Peter.
Yeah, hi. It's just a question about the building, really. It's just a strange concept building that has stairs and escalators. Well, stairs all the way to the top is obvious for fire escape, but why would the escalators be going all the way to the top of the building? Mm-hmm. And also the two lifts, which are on the outside of the building, going all the way to the top, is another strange design concept. Was this a fictitious building, or?
Of course, yeah, this is an image of the analytical model, so they're not actual cases. So in the next step, we would like to confirm by using a real situation by using a real building model. So thank you very much for your good comment.
Excellent, thank you. Thank you for your paper.
Thank you very much.
Always, anything to do with seismic and your work is always interesting. Thank you.
Thank you very much.